Hello, everybody. Now I want to turn our attention towards an often overlooked and always underappreciated part of astronomy, the so-called interstellar medium, which is just a fancy phrase that says it's the stuff that exists between the stars. We often think of all the space that's between the stars as completely empty, but it is not a perfect vacuum. Sure, it is better than any vacuum we have here on Earth, but it is not empty. It contains an aggregate huge amount of gas and a significant amount of dust that then can be used to build stars and planetary systems. So let's go ahead and spend a little bit of time talking about the interstellar medium. So the interstellar medium, I always like to start by taking a look at this dense region of the interstellar medium. This is called the Carina Nebula. And just to give you a sense of how vast the region of space that we're looking at, the scale bar up here is 10 light years. So we're looking at about 50 light years across right here. It also has this in parsecs. And if you're interested in the angular size, this is about 3 arc minutes, which tells you something. We know the distance, so we can translate from angular size to physical distance. But just look at all this action and all this stuff that's going on between the stars. The ISM, while often overlooked, is the source of are typically thought of our most beautiful pictures of outer space, all of our nebulae. And just a couple of things are going on. What you're seeing is this massive complex of gas and dust, this molecular cloud complex, out of which new stars are born. Stars are dying, and as they die, they're ejecting material back into the ISM, which then can be pulled into denser regions of the ISM, which can collapse to form new stars. So the ISM is the hub of star formation and star death. It is a important part of how everything changes, how our galaxy evolves and changes over time. And you can see these dark dust pillars where you have lots of dust is blocking the light. You can see the star cluster where new stars are being born out of the gas and dust that's here. You can see this famous thing that's called the Mystic Mountain, where stars are being born, and a hallmark of a star being born is what's called a Herbig-Haro object. You can see these jets that are shooting back and forth, and here's a jet shooting out. That is telling us that there are stars forming there. You can see all sorts of colors. The ISM has a lot going on. The dense regions are really exciting. That's what we're looking at here. The not dense regions you'd think of typically as empty space, but it still plays an important role. It is a repository of the gas and dust out of which we can form new stars and new planetary systems. It is the area in which whenever a star dies, it re-injects all the material into the ISM. So it is the source of our cosmic recycling. So let's spend at least a little bit of time getting to know our ISM. And what I want to talk about in this video is mostly what is the ISM and what is the stuff that's in it. So the ISM, the interstellar medium, it really is just all the gas and dust that lies between the stars. And whenever we're talking about the ISM, we're talking about the interstellar medium, the stuff between the stars within the Milky Way galaxies. But this could apply to other galaxies as well. You could talk about the ISM of the Andromeda galaxy, the stuff that exists between the stars. Let's take a quick look and we can kind of see what's going on. We can take an inventory of everything that we have in, say, our Milky Way galaxy. Here we're seeing a panoramic shot looking down the disk of the Milky Way. Here would be the core of the Milky Way looking towards the supermassive black hole and its core. But what you're seeing is this is the disk of uh, our spiral galaxy that's flat like a disk, and it looks like a Milky Way. It looks like this milky streak because the stars are so close together that the light gets blurred together. We can't resolve the individual stars, so it just looks like this white blur. If you could have high resolution and zoom in, you'd see that it's made up of billions of stars all so close together that we can't distinguish them apart. So yes, there are stars in our galaxy, but everything that's not a point of light going on in here, a single point, and that's not a star, there's stuff between the stars. And that becomes readily apparent when you look and you see all of these dark dust lanes that are blocking the light from the stars of the Milky Way so they don't reach our eye. So we can already see that one of the things that the ISM does is it obscures our view, or at least invisible light. And what's obscuring our view is the dust that's there. But the dust tells us where the gas is. And we'll go over this again, but I can't say this enough, that we always pay attention to the dust of the ISM because look, it's blocking the light. But by mass, the ISM is 99% gas, 1% dust. Dust is literally the afterthought, it is the very minor component of the ISM. It's a very important component, but it's just 1% of the entire mass of the ISM. Most of it is in gas that we can't see because it's cold and not dense. So there's not very much stuff there that's collected together, and it's not very warm, so it's not giving off much light, which makes it incredibly difficult to detect. That is one of our other videos, is how we actually detect the gas of the ISM. And you can also see that we don't only have these dust lanes that are going on, but you can see there are splashes of color, like these red regions, where you're dealing with the ionization of gas in the ISM. So lots of things going on. But I said I'd give you a complete inventory of the composition. The thing that we really can't see is all the dark matter that's there, but that's not what we're talking about with the ISM. We're talking about the gas and the dust that exist between the stars. Let's take a look at another very exciting place in the ISM. This is the Orion Nebula in the image over here. You can see this with the naked eye. It doesn't look like that with the naked eye. If it did, you'd probably be outside every night on a clear night. Be like, holy cow, the night sky is cool. But with a small telescope or binoculars, you can make out some of the structure of the Orion Nebula. It's the middle star and the sword that dangles from the belt. Uh, you, with a decent telescope, a small telescope that's pretty much accessible. You don't need to be a professional by any means to get your hands on one of these. You can get very astounding images where you can see a lot of this structure, where I think this looks like a hawk or a eagle with its wings outstretched right here. You can see this sort of reddish light that is due to glowing hydrogen gas. So that red light that we're seeing is mostly hydrogen alpha photons, 656.3 nanometers, where we're seeing excited electrons go from the second excited state, falling down to the first excited state, and releasing this beautiful red photon, the visible color of the universe. Here we can see a reflection nebula, and you can see lots of dark dust lanes. So here you can see the gas is glowing in this case, right here, and you can see a lot of the dust. So the space between the stars is not just a pure vacuum, although it's pretty darn close. Even these dense regions are better than most of the vacuum chambers you can have access to here on Earth. So what we call a vacuum on Earth, most of these dense regions, of the densest regions of the ISM, are still less dense than that. But let's talk about the fact they aren't a pure vacuum, but they are better than the vacuums we have here on Earth. What are the densities that we're really talking about? We're really just talking about a couple of atoms and some dust particles per cubic centimeter. That doesn't have a whole lot. If I say, oh, there's about 100 atoms hanging around per cubic centimeters, what does that really mean? How can we put that into context? Well, the air in the room that you're in, that's about 10 to the 21 atoms per cubic centimeter. That's much, much, much larger, 19 orders of magnitude denser. An ultra high vacuum, this is a term that's reserved for our best vacuum chambers, our strongest vacuum chambers here on Earth. The best vacuums we can draw on Earth are still about 25,000 atoms per cubic centimeter. So most typical ISM, the space between the stars, is pretty much this empty space. You're just talking about a few atoms and a few dust particles rattling around. But I can't emphasize this enough. Most of the ISM is gas. A small percentage of it, 1%, is dust. But there is a significant amount of mass. If you take the entire volume of the ISM, pretty much the entire volume of our Milky Way galaxy, and you were to take all of the gas and dust that's there, you're talking about tens to hundreds of billions of suns worth of mass, almost an equal amount of mass in gas and dust as there are, mostly gas, 99%, as there are in stars themselves. So yes, this is a significant portion of the mass of our ISM. All right, so let's just take a quick look. Let's break this down by the gas and the dust component. On the right, you can see another amazing image. This is the MON R2 molecular cloud complex, where you can see dust lanes again. You can see that there's some star formation happening within this cloud and some lights leaking out. You can see young, hot O and B stars, freshly born, that are glowing, and you can see that they're interacting with the gas and dust around them. All sorts of things going on at the ISM that make it really, really fascinating. Yeah, so there you go. You got a couple billion suns worth of mass in the gas of the ISM alone. So you're talking about a significant portion, a significant fraction of the mass of the entire galaxy. A couple of percentage points to tens of percents. All right, not quite half. I might have misspoke whenever I first got excited there. So let's take a look at each component and really hammer in that the gas is the majority of the ISM. 99% of the ISM is gas. And this extraordinary thing, typically, it is very, very, very thin, better than our best vacuums on Earth. The dense regions are rare and confined to very localized areas. So by volume, the not dense regions dominate. So it's made out of gas. What is that gas made out of? Well, it's mostly atoms, and almost all of those atoms are hydrogen. 91% of the atoms of the ISM are hydrogen atoms. 9% are helium atoms, and 0.1% are metals, any element that's more massive than hydrogen or helium. So element number three and higher. This is determined by spectroscopy, and this should be setting off like, oh, I recognize this, I recognize this, I recognize this alarms in your head, because that is the same composition I gave you for stars and the same composition I gave you for the sun. And it'd be the same composition of the atomic, uh, rotating all the atoms of the universe. Almost as if they're all interrelated and that the universe itself is mostly made out of hydrogen and helium gas. So of course the stars are going to be made out of pretty much only hydrogen and helium. And of course the stuff that's between the stars is almost all hydrogen and helium. And it really makes sense if you think that the stars are forming out of the ISM, so they should mimic the composition of the ISM. So the typical density is about 1,000,000 atoms per cubic meter, which is really not that much. I've given that to you in a couple of different ways by now. Let's turn our attention to the dust that is blocking the light right here. You can easily see these dark dust lanes. So this is 1% by mass. And dust particles are much, much larger. They're about 1,000 times larger than atoms. So it doesn't take very much dust to have a very significant effect on light since the dust particles are so large. And I'm saying they're so large, but how large are they really? They're only about a tenth of a micron in size, which is a good thing to picture in your head. Is imagine it's nice and fall. It's a good time to have a campfire or a backyard fire. There's always smoke that's coming up off the fire. Smoke is made out of particles. Those particles of smoke are about a tenth of a micron in size. What are these dust particles? These really tiny microscopic dust particles made out of? Mostly silicates, little bits of rock dust. So little bits made out of silicon oxygen and mix in some other things as well. You have metals and metal oxides. You got things like graphite. You have a significant part of the things out there are these polyaromatic hydrocarbons or polycyclic aromatic hydrocarbons called PAHs. Still trying to figure out what those are really made out of. They're very complex molecules. You have ices that a lot of water ice that coats a lot of the dust particles that are out there. And typically you have about 1,000 dust particles per cubic kilometer. So imagine a kilometer box, so a kilometer on one side, a kilometer deep, and a kilometer high, and then just putting 1,000 of these zero point 0.1 micron sized dust particles in there. That's not very much dust at all, except this dust adds up really, really quickly. If you were to take a meter by a meter square, a square meter, and stretch that out 4.24 light years, so it would just barely touch Proxima Centauri, the closest star to us, that volume would have about 10 to the 19th dust particles, 10 billion dust particles. That added up fast. Outer space is vast. The volume of the ISM is mind-numbingly large. So even though it's not very dense, it adds up to a lot of material. Another way to think about this is Picture our sun at the center of a sphere, and now draw a sphere around that, around the sun, so that it just barely touches Proxima Centauri. So basically, we've just drawn a sphere around the sun that's just what we would think of as empty space. We won't include Proxima Centauri. We'll just go the radius of this sphere is the distance to Proxima Centauri, 4.24 light years, about 4 times 10 to the 13th kilometers. That volume of space in which we just have the sun, using the typical densities, the ISM, the typical dust densities, that gives us enough dust where if we could put it all together, it would have the same mass as Jupiter. So the volume of space is huge. So even as we're talking only about 1,000 particles, dust particles per cubic kilometer, there are a lot of cubic kilometers out there. So it adds up really, really fast. And that's why you can see the effects that it has. And speaking of the effects that they have, I call that a good segue. Good transition there, nailed it. Let's talk about why most astronomers really don't like the ISM. It gets in the way of what they're trying to observe. It blocks the light that we're trying to get, sometimes completely and sometimes only partially, and it makes it complicated because it changes the spectrum of what you're looking at by getting rid of all the shorter wavelengths and making everything look redder in color. Before we get there though, I just have to take a moment. We see this picture all the time, and oh, it makes my head hurt every time I see it, because every time you see this picture, people will go, astronomers have discovered a hole in the universe itself. And I just go, oh my God. One, astronomers, we know, we didn't say that. I don't know why this is such a popular thing. They always almost show this object, Barnard 68. It's not a hole in the fabric of the universe. It's a molecular cloud. It is a dense part of the ISM. It is a cloud, 99% gas, 1% by mass dust, but it's big enough and it's in one of these denser regions where there's a lot of dust there that can block the light. So simply, you have all the stars in the background, and here you have a cloud of gas with dust in it. And there's enough dust to make sure the light can't go through it. So, not as exciting, but that's the truth of it. And with this image, it's just great because it shows and demonstrates these two similar yet different concepts. We have extinction, a photometric effect, photometry. An extinction is just a measure of how much, say, this object, Barnard 68, how much the ISM, the gas and dust of the ISM, how much it is making things appear less bright. It's the overall dimming across all wavelengths. So it's a photometric thing. It is a change in apparent brightness. It's a measure of how much the ISM has dimmed something, made it look fainter. So it is a change in apparent brightness. It makes things look dimmer, which means if we're talking about magnitude, it makes the apparent magnitude larger. Because remember, larger numbers for magnitude means fainter because it's a weird backward system. So it makes it so things appear fainter. It's blocking some of the light that gets to us. Just a measure of how much light is blocked, how much it never reaches our eye, that is what we call extinction. What is making it so the light doesn't reach our eye? Two different things. The first one is the light's coming towards us, and it runs into a dust particle and it gets absorbed by the dust particle. So it never makes it to us. Or it gets absorbed by an atom. So it never makes it to us. So it includes absorption. Another one is the light's coming at you and then it encounters a dust particle and it gets scattered off into a random direction. So it's coming towards you, then went off in a different direction, never reached your eye, so you never saw that light. It was scattered. So extinction is absorption plus scattering, and that together tells us how much light was removed in total. We have 100% extinction in the middle of Barnard 68 here. None of the light from the stars behind it is making it through. We have partial extinction here on the edges because some of the light is making it to us. But you might notice that on the fringes where the densities are lower, so some of the light makes it, it's only partial extinction, everything appears red. And that's because the other effect is a spectral effect. It changes the spectrum, it changes how much of each wavelength of light reaches us. And the way that it works is scattering, that light coming towards you and then going off in a random direction, scattering off dust particles, and scattering off of the air in this room, a different type of scattering. But scattering removes shorter wavelengths preferentially. Scattering is inversely proportional to the wavelength of light, which means that shorter wavelengths get bounced off in different directions more frequently than longer wavelengths. Another way to say that is longer wavelengths more easily penetrate these clouds of gas and dust. They easily go through the dust. Shorter wavelengths get scattered away and never reach us. So, because scattering is inversely proportional to the wavelength of light, the bluer, smaller wavelengths will be scattered more so they never reach us. The redder, longer wavelengths make it through the cloud easier, so the red light makes it through while the blue light didn't, which means that it looks red to us, and that's why all of these stars appear red. We call this spectral effect of getting rid of the blue wavelengths and keeping more of the red wavelengths reddening, because we are very on the nose namers. So the reddening is not the same as extinction, but it contributes to extinction. Is this just telling you how you're removing certain wavelengths? It's really just the scattering component here. So reddening, a little bit more complicated, but it makes things appear redder, and we can really see that if we zoom in. And hopefully this really helps you remember this. So I've just zoomed in on the bottom part of Barnard 68 here. Here in the thickest part of the cloud, where the light's trying to make its way through a whole lot of dust, absorption plus scattering makes it so none of the light makes it through the cloud, and it never reaches our eyes here on Earth, or it never reaches our telescopes. We have what we call 100% extinction. All the light is removed. However, we go towards the edges, we're looking through less material. Some of the light makes it through. If you want to see, say, oh, this star has become so much fainter, 30% fainter, 50% fainter, how much dimmer overall, how is its apparent brightness overall changed? That would be extinction. But it's not completely blocked, so we call it partial extinction. And then you have to consider that, oh, well, the light that's making it through, why is it getting fainter? Well, in part because we're losing all the shorter wavelengths, the bluer wavelengths. We're losing some of the red wavelengths too, but they're better at penetrating through this cloud. So that's the reddening effect. And you can see that the stars that are right here are very reddened as it's going through a whole lot of material. You're losing almost all of the blue and shorter wavelengths. And then as you go to the outskirts, where it's less and less dense, yes, they are reddened, but not by as much. So extinction and reddening. Make sure you go over the notes with those. I do like to emphasize these about the ISM on quizzes and exams. And one last thing I want to talk about with the gas and dust, or really, the gas and the dust of the ISM, is the chemistry that happens on the dust particles. Dust particles are these perfect, ideal spaces for chemistry to happen. Because dust particles are physical little things. They have surfaces. They're solid bits with surfaces. And I'll let my fist be my dust particle here. Here comes my finger, an atom. An atom hits the dust particle. It's going to get stuck to the surface of the dust particle. And that way, that means that over time, this surface of the dust particles is going to start collecting atoms. You will not get chemistry. You cannot get atoms to react with one another if they never get close to one another. And remember how extraordinarily not dense, how thin the ISM is. Even in these dense regions, it's pretty much less dense than our best vacuums or good vacuums here on Earth. So getting atoms together is a very rare occasion, just happening by them floating around. Now, if I put one on a dust molecule and it's hanging out, and here comes another one, and here comes another one, I'm going to be concentrating all of these atoms onto the surfaces of these dust particles, which makes them ideal to drive chemistry. And we can put the chemistry on overdrive when we consider that one of the most common things that's going to collect on these surfaces are hydrogen atoms. I mean, 91% of the atoms of the gas that are collecting under the surface of these are hydrogen. Element number two would be helium. The third most abundant element in the universe, oxygen. So here on the surfaces of these, you're putting hydrogen atoms and getting them together with oxygen atoms, which will chemically react to form H2O, our water ice molecule. So these dust particles will end up coated in a rime typically of water ice. If you know anything about water and chemistry, you know it's a strong driver of chemistry. So these surfaces of dust particles become these little factories, these little chemical factories, and create some pretty amazing chemistry. In fact, and I should finish the story. So you collect all these atoms on the surfaces of the dust particle, you get some really awesome chemistry going on, not only just water, but forming things like ammonia and methane and other simple hydrocarbons, then more complex organics, more complex molecules just in total. And eventually another atom will come along and it might dislodge that molecule, which now you're putting molecules back out into the gas of the ISM. So you have a bunch of molecules that are floating around, and these molecules get really, really complex. The chemistry that happens on these surfaces of these dust particles and then gets liberated into the ISM clouds, the dense clouds that all these dust particles exist in, we have found over 200 different molecules, including sugars, alcohols, both the kind that you can drink and the kinds that you should never drink. And we've even seen perhaps, we haven't confirmed this detection, but there's a strong indication that we have found the simplest of the amino acids, glycine. And that's just a small bit. I mean, there are all the hydrocarbons, your methanes, your ethanes, your butanes, your acetylenes, all sorts of really interesting hydrocarbon organic chemistry going on, more complex aromatic organic chemistry, aliphatic molecules being formed as well. All these PHHs, which are aromatic hydrocarbons. You get things like ammonia, its own driver of chemistry. All sorts of cool stuff happens on these. We've identified over 200 of these. These get re-injected into these clouds. These dense regions of the ISM, this is where we're going to have star formation. And where we have star formation, we have planetary system formation. So if you want to know where the rich molecular universe that ends up getting incorporated into the planets, into things like the Earth and things like us, where is all of this originally being produced? In the ISM, just naturally being produced out there. And I will always like to end this one with, here's a modern list of all the molecules detected in the ISM. You can see that this has been updated in October of this year. So you can see the ones that have been identified in this year. This list gets longer every time I show and give this lecture. Here are the 2-atom molecules all the way up to 12 plus atom molecules. The most common molecule in all of the interstellar medium is the simplest one, molecular hydrogen, diatomic hydrogen, 2 hydrogen atoms that have formed a molecule. But then you can see all sorts of fun. If you're into chemistry, find your favorite molecule on here. You can see a lot of it is organic chemistry. Look at all those C's hanging around, but not all of them. So you get quite a bit of awesome chemistry. And no, this isn't the entire list because there are lots of 2, 3s, 4s, and 5 atoms. So here's the rest of those that you can see. It's really kind of fascinating. I wish I could talk about the ISM for a really, really long time. I have a version of this video ended up being 40 minutes long, so I redid it. It's just way too exciting. It's so often overlooked. I hope you've enjoyed a little bit. We still have a good bit. We're going to try to figure out how we detect things in the ISM. We're going to look at some of the more beautiful objects, the nebulae of the ISM. So there will be 2 more videos on the ISM. I hope you've appreciated it and you won't be one of those people that overlooks the ISM. Thanks for tuning in.